Log on, tune in, find out. Another good idea from Cambridge.
So we're very pleased to welcome this afternoon Simon Conway Morris, who's just down the road, Professor of Paleobiology here in the University of Cambridge, where he's held the chair of Paleobiology since 1995. And I think Simon will be well known to many of us for his work, particularly on the Cambrian explosion, which we're going to hear about later on this afternoon, and indeed many other areas of metazoan evolution. More recently, he's become also well known through his book Life Solution: Inevitable Humans in a Lonely Universe, which I just spotted not only on our bookstall and paperback, but actually at the princely sum of only £11. It started out as a rather expensive Cambridge University Press hardback, but the price is just coming down and down at the moment, so £11 for that I think is a really good deal. I warmly recommend that book, and I'm sure Simon will be telling us more about it. But he's going to start out this afternoon by telling us about addressing the question, is biological evolution inevitable? Thank you, Simon.
Well, thank you very much, Dennis. Good afternoon, and if people haven't said welcome to Cambridge, it's actually quite nice here for once, but come in a week's time and you'll find the snow's up to about here. And thank you also for the plug for the book. In fact, you can get one even cheaper. I noticed on the marketplace here in central Cambridge, there's a second-hand bookstore, and you get one there for £5. So I offered to sign it this morning, but the person who I know a bit, very kindly declined. Well, this is going to be a very short talk, you'll be relieved here, because as you can see, the title is biological evolution inevitable? And the answer to that is yes, so thank you very much. And should any of you perhaps want to sort of dally with such ideas, and I'm very happy not to debate them, but to crush them, such notions as intelligent design, then now, as they used to say in the good old days, when you were on American Airlines were reasonably safe, if your destination today is not Las Vegas, now is a very, very good time to leave the plane. As well. So I will be talking about evolution. It happens, it's real. However, that may not be, as I'll try and explain, the entire story. And the other aspect, which is very familiar to myself as a paleontologist, of course, that I've been very fortunate to work in a number of extraordinary places in the world. I'll mention one of them in the second talk, if any of you are still here. There is only one copy of that book down by the marketplace, by the way. As paleontologists, we are fully aware, of course, that we are standing on a great heap of rocks, which goes back about 4 billion years. We have a pretty good fossil record, and in the Cambrian explosion, I think we're well on the way to explaining how individual body plans are constructed in an orderly and entirely unremarkable fashion, but that's for the future. The things which, of course, interest, I think, everybody in this room are twofold. First of all, as you can see, we've got a couple of sentient, if I get this thing to work after fashion, a couple of those chaps on the top. They are chaps. Sentient species. Somehow, this mush of neurons here allows us to engage in conscious ratiocination, which actually, if you think about it for a moment, whereby lies a paradox, is totally and utterly extraordinary. And that's something which I shall dwell on very briefly. And I think there may be a few straws in the wind as to how we might progress that area. And then linked to that, of course, is we now know that there are more than 200 extrasolar systems. Practically every planet discovered is substantially larger than anything approaching the size of the Earth. Nevertheless, if you extrapolate the statistics of the likely planetary formation in unremarkable circumstances, then there will be millions, hundreds of millions, possibly even billions of Earth-like planets in our galaxy alone. And the likelihood, as I'll try and explain in a moment, is that some of them ought to have life in principle. Whether that's true or not is another question. But more particularly, if they do evolve, I'm as sure as I can be now that they will evolve sentience, and ultimately they should be able to engage in extraterrestrial communication. And there's some problem there, as you're all aware. Because unless, again, there are any aliens in the room at the moment, please put your hands up quite slowly if you have got a hand. Then there's something there which really doesn't add up very well at all. So that's a little bit of the background. There's a couple of other just introductory things, and I'll be going through this material necessarily extremely quickly, typical Cambridge style. You surely understand it, it's simple. But more particularly because I want to cover a lot of ground, but equally I want to try and provoke your discussion, and with any luck, some dialogue in this area. There are some reasons to think, and I'm very happy to go into more detail if required or requested, that first of all carbon and water may be the universal building compounds or building blocks and solvent for life. There are other possibilities. And some people have even suggested, and I think reasonably, that in fact even biochemistry itself may be effectively universal, not only at such a level as here the iconic DNA, but possibly in a number of the other biochemical operations which we see. There's another aspect about the evolution of life which I think is important in this context, because even though not everybody, but the majority of people would still subscribe to the so-called Carbaquist model of life, that is, one based on carbon and on water, and there are, of course, some intriguing alternatives which should not be neglected. Another aspect of this view would be that though life should be very widespread, making complex life, and here we have it in one sense in the Darwinian paradigm of, quote, the eye, is actually terribly difficult. Well, I'll try and persuade you for a number of reasons. I think that's very unlikely. But one thing which is less often remembered, and again, there's a lot of detail in this, is that most of the building blocks, including those we need for sentience and intelligence and nervous systems, actually evolved long, long before those complex organisations emerge. In other words, the molecular substrate you require to make complex things evolves principally in bacteria or other microbes. So if we look at the classic case of the eye, we know that the lenses, and in certain cases a cornea, which are transparent, owe their transparency to proteins which evolved for a completely different purpose, in a completely different context, and have been recruited. Again, only of you who work in evolutionary biology, and this is all second nature. But it's something which is occasionally forgotten. And correspondingly at the back of the eye, of course, we have other proteins which are responsible for the transduction mechanism, and thereby there's a very complicated story, including other things such as vitamin A. But despite all that, that protein has also evolved long before there were any sorts of eyes. So in principle, actually, most of the building yard is already sort of well occupied with things which you would require. Now, I'm afraid I got my slides in very slightly the wrong order. This is a small challenge for me, because this notion, therefore, that complicated things, especially something like ourselves, is difficult to evolve or may require very special circumstances of a so-called rare planet, has also invited a further evolutionary discussion as to the extent to which what would happen if we were to, using Stephen Jay Gould's very famous metaphor, to rerun the tape of life. And of course we can think of historical context of that. This is one of my favourite examples where if things had gone slightly different in 1940, in other words, if the RAF had not managed to defeat the Luftwaffe, then in fact there is a very good argument, I think historically, that in point of fact none of us would be here, simply because at least in Europe our fathers in this country would have been deported to Poland and other places and ultimately murdered. I quite like this slide, partly because it's one of these sort of splendid indications of how to get it right, but also this famous quote from the Prime Minister, and sorry I never get the accent quite right, but it's roughly as follows: never was out. And of course what was the joke there amongst the pilots was in fact that Winston Churchill, when he said never was so much owed by so many to so few, he was actually referring to their bar bills. And this metaphor of running the tape of life is something which would, if taken I think to its logical extreme, and I'll try and persuade you why we needn't do that, is that all these end products we see here, such as, you know, and I'll show the slide in the later talk in a different sort of context, but including even hominids over there, or the chap in his underpants, in other words, on the far left, are evolutionary flukes of circumstance, no more or no less interesting than anything else we might have. Now, I have no objection at all in playing these sorts of games, and this is something historians do, I think, in a very engaging, and I think it's an intellectually worthwhile exercise, and I think it applies also to evolution. So you can see here the essay, in fact, which in this book called What If, where the discussion is what would happen had Britain fallen to the Nazis in 1940 or 1941. In a sequel to this, called More What If, there's another very entertaining essay by a Yale historian who inquires what might have happened if Pontius Pilate had released the carpenter known as Jesus of Nazareth. And in fact, it's a very ingenious exploration of a counterfactual alternative. So, given the cultural circumstances in which most, though by no means everybody, finds themselves, the zeitgeist being one of relativism, as you well know, not in terms of physics, of course, but in terms of moral authority, given the sense we're meant to be free agents, that we can decide exactly what we want to do, this historical resonance, or the evolutionary resonance of almost an infinite number of endpoints, is something which appeals across a very wide cross-section of people far beyond science. And what I'm going to try and show you is that's completely, utterly wrong. Well, Dennis, again, has already kindly given a plug, but knowing that there are a number of Americans in the audience, I suspect so, you don't have to put up your hands, and in particular, knowing how much I enjoy being in America, in particular, because in America, as you know, you can engage in shameless self-advertisement and promotion, and here again, I modestly draw attention. That's my So, in this book, what I'm trying to persuade people is that, in fact, something very much like human is indeed evolutionarily inevitable. I won't be talking about that in any other detail, but I'm happy to again engage in discussion, but I rather suspect that we're alone, and that has not only, of course, scientific implications, but it also clearly has metaphysical implications as well, which might be of more than passing interest. Now, the notion about why we should assume that there is not uniqueness in biology, why we should assume that the number of endpoints, including ourselves, is actually surprisingly limited, would seem to fall at the first hurdle when you go to, for instance, Jared Diamond's essays, where he, as a mainstream neo-Darwinian, wants to argue that indeed evolution is almost completely open-ended. And his route to suggesting that something like a human, which would eventually understand electromagnetic radiation and ultimately develop radios or radio telescopes, must fall at the first hurdle is by reference rather curiously to the woodpecker. But at first sight, being an ornithologist, he would appear to have a good point, because the woodpecker is an extraordinarily designed organism. I'm not an ornithologist, but I think most people are familiar with it because it has this stiff tail, it has this reverse claw here, and most remarkably it has this extraordinary sort of pneumatic skull which enables it to go at the tree like that, and instead of falling unconscious from the tree, continues. Now, Diamond claims that this is biologically unique. Now, I'm slightly embarrassed to tell you here that in fact this is simply not true at all. In point of fact, something very much like a woodpecker, and I'll give you some other examples in a moment, has evolved 2 times more, maybe even more than that. Once in a group of birds known as the vangids in Madagascar, but more particularly in a group of funarids, the neotropical birds. And in certain species, funarids are a very diverse group of birds, I understand, but in certain groups the convergence, that's the thing I'll be stressing, of course, of the skull structure between this particular species of funarid and the woodpecker is almost precise, for a very simple reason. It does the same thing of trying to get insects out of a tree at very high propulsive speeds. And the more I think about it, the more hard-pushed I am these days to actually think of anything which is genuinely unique in biology. Almost everything has been tried. Now, this might be stepping slightly too far towards the end of the talk, but I think there's an interesting corollary to this, because not only would I dispute the fact that evolution is almost entirely open-ended, but also my sense these days is, in point of fact, it's not a question of things working, it's a question that practically nothing works. Almost everything out there is a total and utter failure. It's a very small proportion of biological organisation which is actually functional. Now, in the case, and again, if you're a professional biologist or an evolutionary biologist, these are very familiar examples, but if you're outside the area, and I want to say a little bit, first of all, about convergence in the general sense, give you a few examples, then I'll go on to the evolution sensory systems, because that, in some way, presumably, is a channel towards sentience and intelligence. I'm not sure it's the only one, but nevertheless, it's a starting point. So, to start with this example here, we are mammals, of course. We belong to a group known as the placentals. Both the cow, if it's pregnant, or this girl, when she grows up and becomes a mother, will have a fairly protracted gestation period. There are 2 other groups of mammals, but the one I want to specialise on are, in fact, the alternative main group, the marsupials. And you may wonder why the father's looking so relaxed and happy. Well, he should, you know, because this is his child just down here. In the marsupials, of course, the young is born at a much earlier stage. There are all sorts of complications here. But by and large, they then climb out, well, after they're born, they climb out on the outside of the mother, more or less fuse themselves to the mammary teat here, and then only later become effectively free living as a joey, living in the diagnostic marsupium, that is the pouch. So here we have 2 very different groups of mammals. Here we have 2 very large and dangerous cats. This one coming towards us would have been seen around these parts of the world till at least 25,000 years ago. Correspondingly, this saber-toothed cat, as it is, with these enormous canines here, has a wide distribution across Asia and also North America. And those of you who know the La Brea tar pits, for example, will be familiar with that wonderful museum. This saber-toothed cat here, as you can see, is slightly different, not only because we're seeing it laterally than rather from the front. You can see again it's got the large canine, but this flange here is not present in that area. And in fact, that protective flange is quite a good idea. If we look at the reconstruction of these 2 cats, and again, actually there are further complications in this area which are extremely interesting as to how they actually hunted and so forth, but I don't have time to go into. Both these cats are extinct. So this is one which lives in South America, and this is one which had a wider distribution, more in the northern hemisphere. They are strikingly similar, but as you've probably already guessed, or perhaps already know, there's only one interesting difference between these 2, and that is that this at the top is a marsupial, and this at the bottom is a placental. In other words, the one at the top is much more closely related to a koala bear, or wombat, and the one at the bottom is far more closely related to a giraffe or a hedgehog than they are to each other. So that degree of convergence is indeed striking. Now, the vocabulary people use in the context of convergence is, in its own way, I think, interesting. because typically the words used are uncanny, stunning, remarkable, strange. But why? I mean, this is adaptation. Nothing actually particularly strange about it at all. But I know probably you can imagine, begin to think where that disquiet might actually come from, though not perhaps in the way that it's always thought. Now, I should also say in passing that sometimes people get rather disenchanted with this argument because there are indeed significant differences, especially in the post-cranial skeleton, that behind the skull. And they say, well, really, you're making a false comparison. This convergence is not exact. But my answer to that, I'm afraid, is rather straightforward, and it is, effectively, that it makes absolutely no difference whether you're eaten by the cat at the top or whether you're eaten by the cat at the bottom. It really doesn't matter at all. No, it's not the way you go. So that's one example of convergence. Now, another one, which is actually quite interesting, again, I can't go into all the details because of the time, is that in this mammal marsupial placental convergence, we find a very intriguing parallel within the birds. Again, there's a lot of complications here, there's a lot of complications about the molecular phylogenies of birds, but effectively you have a relatively primitive group of birds here, which are sometimes known as the metaravians. They're shown on the respective left-hand sides, and you have a more advanced group on the other side. Now, I don't have time to go through all the differences, which are known as the coronavians. And let's just take this one, for instance, I and J as one sort of example. There we've got a tropic bird and a booby. The degree of convergence between these two is really very striking. I'll just give you one example. They're both tropical hunters who go after squid with flying fish. They have to hit the ocean at a high velocity, and to prevent their skulls being smashed in, they have these special air sacs, a bit like our air cushions in the cars, which protect them from the impact. Both those groups have evolved it. Again, from an adaptational point of view, what's surprising about it? If you're going to hit the ocean at high velocity, it's a very good idea to have those sorts of things around you. But in all the other groups here, things close to owls, things close to loons, things close to bitterns, things close to flamingos, things close to hudsons and so forth, we have this remarkable correspondence. And if you look at the relative diversity, that is the number of species you get in the placentals versus marsupials, you have very much the same arrangement here. And in essence, and I'm thinking about this from some other bits of work which I don't have time to talk about at all, when you keep on arriving at these forms, again, not identical, but, quote, remarkably similar, you begin to get the sense about the way in which morphology almost crystallizes into particular forms. And any one of those has an immediate functional explanation, which is entirely explicable by processes of natural selection. But it does, I think, reiterate my sense about the question as to how many things actually work in the universe we have versus the great majority which probably don't work. So that's another sort of parallel which suggests, and I think quite strongly suggests now, that there may be some big, deeper patterns of organisation in biological diversity. And after all, biology, the first approximation, is pretty free of rules and laws. It's not like physics and chemistry. We don't have a periodic table. We don't have things like general relativity. We just have an unholy mess. We have lots and lots of exceptions, apparently. But this sort of approach begins to say, well, maybe we can find ways in which we can formulate a more formal arrangement of argument. Now, in terms of other sorts of convergence, I just want to touch on two more examples because they are at opposite ends of the spectrum. By and large, because we're whole organisms and because we are vertebrates, examples like saber-toothed cats, examples like birds are moderately familiar. But in point of fact, the convergences can be demonstrated from the molecular level all the way through to levels of behaviour. And I'll give you an example of each. Molecular convergence should be extremely surprising for the simple reason that we have a number of building blocks in a protein, effectively 20, 21 amino acids. A typical protein might have 500, maybe more amino acids, and therefore the combinatorial number is gigantic. It's far larger than the number of elementary particles in the universe. You know, astronomers, let me remind you, deal with very small numbers indeed. Biologists deal with big numbers. Oh yes. So if indeed you found two molecules which were identical, and you knew beyond all reasonable doubt from other evidence, had separate origins, then actually I would stop believing in evolution, but of course we don't see that. But nevertheless, we do see a convergence of a particular sort, which I think, again, is interesting in its own right, but also suggests that there's some predictability in the sorts of things we're trying to do. And again, biology doesn't believe in predictability. It just says random, mutation, random, mass extinction. And the example, I give you a whole lot of examples of that, is to do with an enzyme that's a natural catalyst which accelerates chemical reactions by many, many fold. And this particular one is responsible for dealing with carbon dioxide and its dissolved equivalent, bicarbonate. Now, carbon dioxide is effectively the storage of carbon on this planet in one form or another, either in dissolved form or in limestone. To get hold of that, you have to use this enzyme known as carbonic anhydrase. And this is the sort of thing you have in your bloodstream. If you don't, you're going to be seriously ill quite shortly, because it deals with carbon dioxide from respiration. It also deals with the construction of bones. It's also used by plants in photosynthesis, because you've got carbon dioxide and water, which combine ultimately through a very complex process to produce sugars and oxygen, effectively. I would have thought, intuitively, that given that all life is carbon-based, probably all life comes from a single cell. Once you've invented carbonic anhydrase, that's it. You keep on using it again and again and again, but you don't. In point of fact, carbonic anhydrase, this enzyme, has evolved independently at least 4 times. And the trick in the convergence is that little blue dot there, the single one in the top, 4 here and 3 there. These are 3 of the 4 times. And the convergence lies in the fact that in each case you're using a zinc atom, and it's got in association it amino acid residues, typically histidines. That's not at all surprising, but there are 1 or 2 exceptions to that. So that if you want to deal with carbon dioxide as a Carbaquist form, you will invent carbonic anhydrase. In other words, I think we can be sufficiently confident now to suggest that wherever there is life in the universe, it will be using zinc in that coordination as carbonic anhydrase. And I think, you know, as soon as you think about it, it's not actually terribly surprising. But that's the sort of thing which I think is sometimes slightly neglected. Let's look at the opposite end of convergence. Sorry, it's a slightly slow on the thing. Come on, so. That's it, well done. You can see why it took a bit of time to appear. If you consider the way in which humans get drunk, you can make a very interesting comparison to the way in which fruit flies get drunk. Why do fruit flies get drunk? They don't get drunk in the way that we enjoy a Bombay Sapphire with a little bit of tonic, not too much, that's most important. It's because they have to deal with a fruit substrate, fruit flies, which will tend to ferment and produce, as we do, of course, under controlled industrial conditions now, produces alcohol. So therefore they have to have tolerance to alcohol. So what you do is you take your fruit flies and you put them into a special machine, and I'm not joking, I never do, as you may have realised, known as the inebriometer. And this has got about 500 fruit flies in it, and you saturate their atmosphere with alcohol. And then you study how fast their legs move. And every time the leg moves, it crosses a light beam and that registers. So this here on the vertical axis is the speed of the legs moving. Now compare it to what it's like at a cocktail party, okay? Everybody arrives, we hope more or less sober. Fine. In fact, the first drink goes like that, and a roar of conversation. So the legs are moving all over the place. But then there's panic, because the first dry martini's run out. There's no sign of the waiters. They don't seem to be anywhere. The conversation drops like that. But then, thank goodness, the second one arrives, and then there's another surge of activity there. But as more and more is drunk, at least in the case of the flies, the end point there leads to death. So in this way, this is nothing to do with the genetics of alcohol behaviour in these organisms. Actually, they're quite similar. It's to do with the behaviour of these particular ones. Once again, is convergent. So when we're looking at the sorts of convergence, the final thing worth stressing, I think, is, and this is something which all biologists find extremely difficult, and I can quite see why, because I'm very keen on fossil worms, as it so happens, and that's what I spend my professional time doing, and they come again in all sorts of shapes and sizes. And you tend to be very impressed by just the sheer disparity, the sheer diversity of forms. And if you think of the octopus, and I'll come back to that in the context of the eye in just a moment, from H.G. Wells onwards, and probably before, I've checked what Aristotle wrote about it, but in terms of what would look most alien, then one would take something like the octopus with these writhing tentacles and all the rest of it. But even if we consider the tentacles by themselves, if you take high-speed photography of these tentacles, it turns out, in fact, that the musculature of these things operates in such a way as to form natural joints. Effectively, waves of muscular contraction move in opposite directions. When they meet, they define a joint. And if you then look at the definition of the octopus arm up here, in the blue, the black and the red, where those joints typically form, and there's some interesting statistics here to show there's a constant proportion between principally the red and the black level there, that thing is operating in exactly the same way as our arm. Yes, it is a short-lived hinge for a short-lived purpose, but the whole biomechanics of that, even though it is based on a muscular system which is completely unlike the muscular system of our arms, has converged on the same array mechanism. This is a very nice paper. It was published in Nature a couple of years by Sombre et al. And they have a wonderful paragraph at the end, and you can see them more or less scratching their heads and saying, well, maybe this is the only way we can do it. this may be the optimal solution for this sort of operation. And that, again, needn't surprise one particularly. There's been further developments in this area as it happens, and it's not always as straightforward or as simple as this particular example here. But again, it's this thing of going below the skin deep. And I could give you a comparable example when, for instance, you compare the swimming activities of sharks, especially the laminid sharks, and a tuna. There's a fine paper written by Donnelly et al. In Nature a couple of years ago, and the title is More Than Skin Deep. These things look superficially similar, but once you actually go down, the whole organisation of the thing is operating in a remarkably similar fashion. So then, let me just rattle very quickly through some of the fairly well-known examples of convergence in sensory systems, because as I mentioned a moment ago, I think this is important, because in some way, and we don't know at all in any detail, this underpins our operation of sensory modalities, and in some sense, sentience. And there's a very interesting work there in terms of various equivalents at higher levels, which in fact may be much more similar than is generally thought to be the case. So, we of course are descendants of the fish, and not surprisingly we possess the same sorts of eyes. That's a rule of thumb, not always, but the rule of thumb in evolution. And this is based on a so-called camera design. As I think most of you will know, in the squid, the octopus and the cuttlefish, the group of mollusks, which are called cephalopods, there is a remarkable convergence between the eyes of ourselves and the eyes of these mollusks. We know from molecular biology, we know from paleontology, we know from embryology, that these two groups cannot possibly be closely related, and we are beyond all reasonable doubt, in fact we're working on some of these fossils at the moment, that the common ancestor of these creatures could not possibly have possessed this camera eye. This animal here, the cuttlefish, of course, has a close relative to the oyster, and as most of you will know, in point of fact, one of our close relatives is the starfish, for example. So they both navigated to very much the same solution. And when we look at the details of the lens, for instance, again, I don't have time to go on into all the details, but one of the important things you have to do is correct what's called spherical aberration, slight curvature of the light according to your impingement on the surface of the lens. And not surprisingly, if you do have spherical aberration, you will not have a finely focused image. If you ask a physicist what is the ideal solution, they'll produce that parabola for you, and you can see that both the octopus and the trout independently have arrived at very much the same solution. As it so happens, the proteins they use are completely different. And again, as soon as you stand back a moment and sort of scratch your head a bit more, well, how else was the world ever meant to be? I mean, it's not actually terribly surprising, but it does again suggest that not only are these systems going to be convergent, but they will be convergent in certain cases in extremely sophisticated ways. So when we take a cross-section through these eyes, one sees that they are indeed strikingly similar. It is essential, perhaps, for a few people here to be reminded that in every case evolution has a footprint. In this particular case it's shown most clearly, but there are other evidence that the relative position of the retina in the central panel of the cephalopod, the octopus, is reversed in comparison with us. The reason that's perfectly straightforward, because the retina of that group is formed by skin sinking inwards, whereas our retina is a product of the brain going outwards. That explains why they have an inverted position in our cells. Slightly less well known is that if you go to other groups now, on the left we have a relative of the earthworm, it's a marine form. That too has also independently evolved a camera eye. The camera eye has actually evolved independently something like 7 times, including even in some jellyfish, and thereby hang some utterly extraordinary stories. But the interesting thing is that these animals which possess camera eyes tend to hunt for meat, they tend to move fast, and they tend to be intelligent. So that's, again, not a surprising combination. But why that matters should be apparent when I show you this picture, because of course there are many sorts of eyes, there's more than 40, but the most principal ones are our camera eye, or the alternative, the compound eye. The compound eye, as you can see, is made of many lenses, is characteristic of the insects, but has evolved independently at least 4 times. The point about the compound eye is it does have some relative disadvantages in comparison with the camera eye. You can pack so many lenses on. You can make the lenses to a certain size but no smaller, otherwise they won't act as waveguides. And you of course have a surface which can only accommodate a finite number of lenses. And you can do a thought experiment, as indeed Kuno Kirschfeld, a physiologist who works in Tübingen, has done, to simply say, well, supposing, for the sake of argument, that God had forbidden camera eyes, what size of eye would we require to enjoy the visual acuity we do if we were forced to use a compound eye? And the answer is pretty sobering, I have to say. I wouldn't want to be in this sort of predicament at all. You'd actually need an eye possibly 10 metres across. And again, in the way that one has with carbonic anhydrase, I think there's a point of predictability here. Now, Baker's point elsewhere, in other circumstances. But if we're ever visited by the extraterrestrials, if the spaceship lands and the ramp comes down and they all come down with laser cannons trying to shoot you, if they're coming towards you with compound eyes, don't worry at all. They probably can't see you very well. But if they're coming towards you with camera eyes, you must run away as fast as possible, because they'll say the biologist told us to be careful of those people. And they'll also have things like irises as well, but that's another story. If you want to be interested in that area. So, the visual side, of course, is one which we accentuate because most of us regard that as our primary sense. There are, however, some very intriguing comparisons in terms of completely different systems. Again, I'll just mention these in passing. If you look at the star-nosed mole, for instance, the periphery of the nose is modified into this tactile set of tentacles which are extremely sensitive to touch. The basic neurobiology of that touch system, that tactile system, is actually extraordinarily similar to an eye. Ken Catani has said this is a mole which uses its nose to see. And of course, as soon as you think about it, there's nothing very strange about that, because of course you and I aren't seeing each other, we're making interpretations of each other, and all of us get very quickly bogged down into sense perceptions, what the philosophical implications of that might be, and I think there are various ways we can fight our way out of that corner. But the fact of the matter is, there's no reason why any sense input can't provide effectively an equivalent image. And even things which to us look quite alien may in fact be far more similar to ourselves at that level of convergence than one might at first expect. And then if we look at actually the relative sense areas in this star-nosed mole, not only the nose itself, but also the forelimb there, are also heavily endowed with nervous tissue. In point of fact, in the star-nosed mole, something like 5 times as many nerves go from its small nose to its brain than go from our entire hand to our brain. So you can get some sense of what the sensitivity of that thing must be. It's effectively a tactile retina. Not only is it a tactile retina, but it even has a specialised area endowed with even more nervous tissue, which in our eye we call the fovea, and there's an exact analogue of that also in that mole as well. Even more alien systems of sensory perception, such as those which involve the generation of electrical fields. This is best known, though, it's not restricted to fish, and there are many such examples. One of the most compelling convergences we know of at the moment is that between the fish which live in Africa, the so-called elephant-nosed fish, I think the name is self-evident, and those which are found in South America, the gymnoted fish there. Both of them, again, is a long story here about many similarities, but both of them have effectively arrived at the same solution of not only living in an electrical world, but being able to navigate in total darkness, to be able to engage in courtship, to engage in recognition, even to jam each other's signals, which is something we find in an analogous way, of course, in certain cases with bats. And there too, if one looks at the basic sensory perceptions, there's no more reason to doubt that they are making their sense around them in just the same way as we are using our eyes, at what is fundamentally a very similar level. And that's also true, of course, when we go to echolocation. So, for instance, echolocation is best known in the bats, but of course it's evolved independently at least twice other. Once in the dolphins, they're shown in here, but also in the birds at least 2 times, in the oil birds and in the Asian swiftlets. In these sorts of cases, there's an additional level of inquiry, because at least in the case of the dolphin, there's experimental evidence that suggested in ways which we, I think, find quite difficult to comprehend. Somehow they are combining the visual information and the echolocation information into effectively what we would probably say is a single image. And that too is important, because when we then go on to the general discussion, which was put forward in a very articulate fashion in Thomas Nagel's famous essay, What is it like to have the mind of a bat, which I think to some extent restarted the interest in consciousness, and of course I think to the first approximation, along with the study of the origin of life, that is a total graveyard of ambition. You know, if you've got a really clever young person and he goes up to you and says, I'd like to waste my life, what can I do? You say, go and work on consciousness. You know, they say, no. If they think they're going to get to the answer in the way that some of my distinguished colleagues are attempting to achieve, they may be right, but I think they're not going to be very successful. But Nagel's argument was that effectively we cannot know the mind of the bat. It is utterly alien. It's completely different to us. It's based, as I say, on echolocation and the like. And therefore it will remain entirely unknowable. And that actually is not so far removed in a way from Colin McGinn's argument to do with consciousness, if I understand them correctly, which is that in a sense, and this is actually, I think, echoed in Nagel's own essay, that it's actually beyond our comprehension. You know, there is a neural substrate which in a sense does not allow it to understand itself. And they may be right. They could well be right. but I'm not sure that's going to be the case either. But at least from the perspective of convergence in evolution and the convergence of sensory systems at various levels, there is some reason to be optimistic that we are basically talking about the same thing. We don't know what that same thing is, but nevertheless it is not completely different. And this applies, I don't have time to go into this area, there's a group of heretics at the moment who are talking quite seriously about chemical communication in plants, and if I have to remind you that a good part of our brain activity is not electrical, it's chemical, then one can step back slightly and say, well, are you so sure that plants aren't conscious? Of course they're not in the sort of Prince of Wales tree-hugging way. I'm not thinking in that sort of New Age stuff. You know, I love my oak tree and that sort of business. But it may well be, and we already have some information about that, in terms of the exchange of information between plants, for instance when they're being attacked by predators, that possibly we should just stand back very slightly and, dare I say, be a little bit more imaginative. So that's one aspect of what may be leading convergence in one set of directions. Come on, a little bit slow. It's back. It's going to have the mouse for dinner. They don't want to see the next slide, do they? Everyone look away. Try that one again. There we go. One other aspect of neo-Darwinian thought, in addition to the notion of, quote, woodpeckers being unique, and therefore, in final analysis, everything being unique, which has been very much a theme of discussion, and one which has been articulated especially clearly by the late Stephen Jay Gould, is the importance of mass extinctions. Because why do we know that this diagram here is impossible? And I should say, in parenthesis, very unfairly, I call this the degree ceremony, the graduation ceremony in Oxford. Yes, yes, look at all those dinosaurs, there they are. You know who that is? That's right, he wrote a book recently and sold very well. That's right, yes, very good. We know that the dinosaurs weren't domesticated simply because 65 million years ago on a June day some clown dropped a large rock on the sky, and perhaps some of you saw the paper in Nature the week before last arguing we now know basically when the asteroid was formed as part of a wider collision event something like 60 million years before the impact itself. And this led to the disappearance of all the great reptiles, not only those on the land, the dinosaurs, but also those in the seas, things like mosasaurs, and also those in the air, the pterosaurs. And therefore, briefly going back to our bat, as Gould and many other people have pointed out, that would have denied forever, if the asteroid had missed, the ecological opportunities which are then seized by the mammals and also the birds. So we wouldn't have had the sky being re-invaded by the flying mammals, the bats, nor would we have the oceans re-invaded by the cetaceans, and I'll come back to them in another moment with regard to the dolphins, nor, of course, would we have had the evolution of the great apes, and I'm horrible thing that's going to appear in a second. So their history seems to have been completely diverted into a completely new direction. And if indeed the primates hadn't managed to radiate, and thereby the great apes, and thereby us, that direction of evolution would have been forever forbidden. Now, I think historically that is superficially correct, but I think in the longer term it's most unlikely to be correct. And the reason is that we can still engage in counterfactuals. And on this planet, and I think all Earth-like planets, you're going to have ice ages for various reasons, and mostly linked to greenhouse gases, effectively. So imagine the asteroid misses. We go into an ice age, so what happens? The temperate and the polar zones are much cooler. There's the sorts of places where warm-blooded organisms, they're called birds and mammals, by the way, which coexisted with the dinosaurs, are going to begin to radiate. The tropics remains full of dinosaurs, that's okay, they like it, so do snakes and lizards today. The tropics are poaching with those reptiles. But, as I'll show in a moment, because these socially adept, warm-blooded forms have an ability to invent independently technology, and amongst that is also a craving for protein, then I'm afraid the mass extinction of the dinosaurs will be getting underway about 30 million years behind schedule. It'll be a different sort of mass extinction, but it's basically equivalent to the mass extinction which went on in Australia and South America in particular, led to the destruction of the large mammal faunas, to some extent in Africa as well. Now, when we consider the birds, it's now becoming quite clear that the degrees of convergence between themselves and ourselves are much more exact than had been thought. I start, of course, with this slide. You'll all recognise it straight away because there aren't many places in the world where you get penguins and horses living together. And this, of course, I want all the English here to put their hands on the heart at the same time. Thank you very much. This is the Falkland Islands, very important too. And in the case of the birds, they have independently involved warm-bloodedness. ourselves. They're, of course, effectively feathered dinosaurs, so it appears. The molecular mechanisms are very similar, but not identical. But it is arguable that if you want a large brain, if you want a stable body state, then you really need to have a very precisely controlled temperature, and you need to elevate that temperature as well, so you can have reasonably fast chemical reactions. Another thing which is now clear is that not only have birds learned to vocalise and sing at least 3 times themselves independently, but the neurobiology and also the process of how they learn to sing is remarkably similar to the way in which we learn to speak. They don't have language, that's a slightly different point. But nevertheless, it seems that there's probably only 1 or 2 ways. If you're going to sing wherever you are in the galaxy, odds are you may end up singing much as we have to sing and the birds. Correspondingly, this is something which has only become clear in the last few years, something which is very widespread amongst the mammals, something which we take for granted, but in fact is, again, from one perspective very strange, is what's called social play. Now, if you look at the more intelligent of the birds, especially the crows, and here a high-altitude parrot, this is known as the kea in New Zealand, these show a one-to-one match in the categories of social play which we recognise in the mammals. So, for instance, we have tug-of-war, we have mock wrestling here, and the kea is particularly interesting because as young they go around as delinquent gangs, trashing things, and here you can see them dismantling an armchair. They also like taking cars to pieces. The ideal is to actually take out the rubber here, and then if possible, if the window falls in, then they jump into the car and continues to trash the interior of the car. And for some reason I can't put my finger on there, rather unpopular in New Zealand. I don't quite know why, but there we are. But this social play is convergent on our social play. And in particular, why that matters I think will become clear in a moment, because there's one other context I need to mention. And that is that in addition to those convergences, we also now have compelling evidence for convergences in tool making. In the New Caledonian crow in particular, here in the wild they use these probes to extract insects, and they also make hooks there. This tool making is substantially superior to anything which a chimpanzee can do. And it's just been shown, I haven't had time to read the paper, that in certain circumstances the New Caledonian crow uses one tool against another tool to achieve its purpose. And why this matters is, you can see, we've got here the stripping out of these pandanus leaves to produce these successive probes, and if I have the slides in the right order, I hope I do. I want to make sure. These are successfully modified to produce, let me try that again, sorry, there we go. Yeah, thank you. These are successfully modified for different functions. That's a proto-technology. And then if you consider the sort of tools we were making 2.2 million years ago at the beginning of the older world cultures, it's not entirely clear to me that they're very much more sophisticated than these. And this, again, has been arrived at completely independently. So why does all this matter? It matters, first of all, because it seems that the cognitive landscape which the crows, in this particular case, and also the parrots are building for themselves, which can be divided into such things as imagination and causal reading and flexibility, really maps very closely indeed with the apes. There's some very interesting work being done here in Cambridge on especially the scrub jays. Sorry, I need to go back. I think I've lost a couple of slides, I'm sorry. The other thing which is not clear, I'm sorry, I'm not too much of a rush when I get these things together. The other thing which is, no, never appeared. The other thing is that if you look at the brain structure of the bird brain, it is completely different, for all intents and purposes, to the bird structure of the mammalian brain. In other words, we have effectively a laminar structure, whereas the birds have what's called a nucleus structure. It's a nucleate-like structure. And there's been a lot of attempt, first of all, to find homologies between the two sort of brains, and that's not been very successful. And in addition, it was then thought, well, maybe birds are effectively sort of piling one reptile brain on top of another, and that's also not correct. So what this means is, and I think this is very important, is that the cognitive landscape which emerges from the bird brain is indistinguishable from ours, and yet it comes out of a different sort of brain. And then you have to step slightly backwards and say, well, that's all fine. I mean, brains do thinking, don't they? But it's not quite clear whether they should have the same cognitive landscape. But you can then stand slightly back further and say, well, where exactly is this, quote, landscape coming from? And again, you can understand that we're beginning to touch on the rather tricky area of what is consciousness. And it may well be that there are particular molecules which simply allow you to be conscious. That'd be a nice idea. I'm not quite sure what they look like, but nevertheless, that's an idea worth playing with. And if those molecules are in common, that's fine. We've solved the problem. But you'll see, I think, that that sort of regressive argument leads you into, I think, some pretty implausible corners without a great deal of trouble. So there are those aspects about the convergence between ourselves and the birds which I think are relatively understated, and in a way analogous to the octopus arm and our human arm, or octopus tentacle and our human arm, actually point at a deeper similarity. Now, to move on very quickly, there are other aspects about convergently cognitive states which at first sight might seem to be less surprising, but in point of fact I think in their own way are more compelling. More intelligent birds do tend to have somewhat bigger brains, but oddly enough, flightless birds, think like an ostrich, is by some people's estimation one of the dimmest animals on the planet. You know, just because you chuck away your wings and don't have to worry about body weight, they do not get disproportionately large brains. It has also been claimed, especially by Stephen Jay Gould, but others, that this increase on our own brain size from around about 6 million years ago, here effectively shown with an Australopithecine and then Homo erectus and then ourselves, is a unique evolutionary trajectory. And again, this is important because it's an echo of the woodpecker argument. It says, well, sure, we end up with this colossal brain at the end of the day, which allows us to do things like string theory or write poetry. But as Gould himself would have said, this is all a spandrel, this is all a glorious accident. You know, it's interesting we can do these things and we should be pleased that we can actually study evolution, but there's no intention in that. And of course there's no intention in it per se. I don't think there would be for a moment. But it's not the case to begin with that this increase in brain size is unique. In point of fact, if we look at the toothed whales known as the dolphins and the porpoises, it turns out that their increase in brain size was achieved substantially earlier than our increase in brain size and has been maintained for perhaps 15 million years. Why do I use the word maintained? Because the brain is effectively an evolutionary disaster. Nobody in their right mind would invent a brain. It sucks up energy at an extraordinary rate. Well, not only does it suck up energy, all of you had lunch, those of you who did have lunch, would be using 20% of your lunch to get 2% of your body mass going. So it's not the sort of thing which one would normally invest heavily in. So if we see the increase in the brain size of the hominids shown in the red dots there, you can see that in point of fact, only about 1.5 million, let me get this thing right to work, only about 1.5 million years ago, that's the thing that's got a light in its own now, and I'll keep on flashing on and on. I want you to look at that point there, Mr. Williams. Thank you very much. Did the dolphin brains actually? Did the human brains actually pull beyond the dolphin brains? Before that, they were the animals with the biggest brains on the planet. Is that interesting in terms of convergence? It most certainly is, because they show again all sorts of similarities in their cognitive landscape. Rather surprising, despite the fact they don't have hands, they can use tools. This is a female dolphin in Shark Bay, and it and its daughters learn how to put sponges onto the front of their rostra, probably to provide defence when they're grovelling around in the gravel after food against such poisonous things as sea snakes and stonefish and things like that. And more particularly, when we look at the entire cognitive world of the dolphins, epitomised here in this playfulness when they blow these sort of bubble rings through their blowholes here, with their ability to memorise things, their ability to communicate, their ability to recognise themselves as mirrors, which we'll come back to in a moment. There's every reason to think that these things are not only, that these animals are not only highly intelligent, but again are occupying a cognitive space which is very similar to the apes and to the crows. And you might then stand back reasonably and say, well, so what? They're mammals, aren't they? Well, I'm not so sure, because after all, you know, crows and apes live in trees, and you could imagine them making a cognitive world which is broadly arboreal. Whereas if you're living in an ocean, in a completely buoyant environment, where you depend very largely on echolocation, you might say ab initio we would end up with a different cognitive landscape, but we don't. Once again, we end up with something which is very similar. Now, there's one other aspect about animal cognition which I just want to touch on for a couple of minutes, which again I'm finding very intriguing, before I go on and quickly finish Act 3, if possible, Dennis. Yes. And that's to do with the elephants. Now, the elephants are very interesting for a number of reasons. First of all, their trunks are effectively the answer, perhaps, to their intelligence. Because it may be that because they are so manipulative with their trunks, this extended nose, that might have been the trigger to their cognitive exploration. And although there's much emphasis in terms of human evolution on cognitive superiority emerging through social interactions within the horde or the group, there's as much reason to think that the spur towards intelligence is to do with the manipulation of tools and other objects. So that's one interesting thought. The other thing, just in passing, is that if you look at the kidney structure of the elephants, so I'm told, it's strongly indicative that the elephants had an aquatic ancestry. And why, therefore, did they have trunks? Because the trunks initially evolved as natural schnorkels. So that, again, I think it's a very real possibility. But when we go and look at the elephants, there are a whole series of interesting aspects about them. They use tools. Here we have them using fly whisks to keep off parasitic flies, and that's no joke. Those flies will take litres of blood. And the great advantage of these tools, both by the baby here and the female here, is that once you've used the tool, you can eat it, which is relatively convenient. And also, they are capable of mirror self-recognition. Once again, from the human perspective, this is something we take completely for granted, but it's quite, and if you live with animals, it's generally a little bit more familiar, but it's quite difficult to understand, you know, the leap which we take entirely for granted. Of course, you need an elephant-sized mirror, but what you have here is you put a marking on the elephant there, which you have every reason to think it can't smell or otherwise recognise. And then you see the elephants beginning to investigate themselves, and this is the moment where it dawns on them that there's not another elephant behind the mirror or anything like that. That's me. But bonobos, possibly parrots, dolphins, elephants ourselves, is a very small list, but again, you could see from the point of view of cognitive understanding, if you're starting to move into new worlds, which clearly we're doing now, and this is one aspect which from our perspective is, you know, natural and simple, but seems to involve something connected to intelligence, but there may be something beyond that as well. And the other thing about the elephants, which is very interesting, is that very unusually, there's some evidence from dolphins as well, they have a curious fascination in their own dead. Not any old bone, but especially the ivory, as well as the bones of the elephant. And in addition to that, their reaction both to the death of their young and also the matriarchs. This is a matriarch in the process of dying in Uganda, and there's a sequence of photographs from this paper showing the other one trying to lift it up and so forth. The curiosity, the interest, and for want of a better word we would call grief associated with the clan behaviour, not only of the immediate clan, but sometimes unrelated clans, is again something which, you know, from our perspective, you know, it is awfully familiar. But it seems to be effectively arrived at independently by at least one other group. So, quickly to conclude, what would be a tempting possibility, I don't know if it's actually going to work out this way, is to say, well, yes, this is all jolly fascinating, at least I hope you find this interesting, but there's still no doubt, as I think is epitomised in this picture here, you know, what other species would regard this as a sensible thing to do? You know, you have to give it, I mean, again, because we're so embedded in what we regard as the natural world around us, it's sometimes easy to forget how extraordinarily strange we are. We're most peculiar. So dropping out of balloons is regarded as fun by some people. And the notion would be that maybe there is, you know, a genetic change which makes us human. Well, France may, in fact, have evidence of that. I'm not aware of that. Maybe there's one particular, you know, polysaccharide in the brain which just tips us over in a particular direction. But I think there's evidence against that. And the lines of evidence really come from two areas, and then I'll finish. The first is to do with the Neanderthals. The Neanderthal there on the left is almost certainly a central species. By and large, the Neanderthals, which died out around about 25,000 years ago, have been regarded as runners-up. However, they had, if anything, a slightly larger brain than ourselves. They also had precision grip. There we've got a Neanderthal finger and thumb coming together, and that's not very surprising because we know that they had tools. We know that they made fire. They almost certainly had clothing. And in addition, as I'm sure most of you are aware, curiously they buried their dead. Now, of course, it's a complete matter of speculation why they may have done that. But in fact, the oldest hominid burials are Neanderthal, not Homo. As it so happens, this is the famous burial from Kabara in Israel, and the skull itself has been removed. Again, for what purpose? If any purpose, we have no idea at all. But as I said, the Neanderthals are extinct, and the general idea is that they failed either because of climatic conditions, there's a paper in this week's Nature discussing that, one of my friend Cronus in Leeds, or possibly due to interaction with Homo sapiens. And some evidence for interaction with Homo sapiens might come from the fact that shortly before the Neanderthals do disappear, and the Neanderthals are effectively a European species, they undergo this remarkable cultural revolution, which is sometimes referred to as the Chateauperonian cultures. These are teeth and bones of fox and other animals which have been drilled or incised, and although they've not been found like this, in situ were most probably some sort of necklace. The common understanding has been that this cultural revolution, which was undoubtedly in the hands of the Neanderthals, was the result of contact with Homo sapiens, which was moving in from the Levant and other areas of Near Asia. That may be true, but there is another possibility which is based on controversial work on radiocarbon dating, on cave stratigraphy, and also preceding Neanderthal cultural types, to suggest that this Chateaubriandian culture was arrived at completely independently of ourselves. Now, once again, it's a little bit like the elephant mirror self-recognition, because we're used to so-called extra, so all of us are wearing clothes for all, obviously we're hiding our nakedness, that goes without saying, but we're choosing our colours, we're very often making deliberate things, either to make the paunch very, very slightly smaller, or sometimes very much larger, but one's dealing with things where you're communicating all the time aspects about yourself, your status and all the rest of it. That is something which is happening to the Neanderthals. Now, if that is happening independently, whatever that necklace was used for, whether it's for sexual attraction or shamanism, who knows, we have not the foggiest idea. That's the sort of idea that you are going to end up with highly advanced cultural states independently. I'll skip that, we may come back to that if necessary in any discussion. The other straw in the wind, which is very interesting, is that, as in any area of science, again and again, just when you think everything's sorted, the textbook's just gone off to the press, something totally surprising turns out. This is, again, quite well known, I'm sure, to the majority of you. Here, of course, we have the Indonesian archipelago, and as I'm sure all of you know, in this little island forest here, there have been the most astonishing discoveries in the form of a diminutive hominid, nicknamed Hobbit, being something in the order of a metre in height. And this diminutive hominid, Homo floresiensis, everything hunted, everything had fire, lived from at least 100,000 years ago to possibly as recently as 12,000 years ago, coexisted with Homo sapiens, but the brain size is smaller than that of a chimpanzee. Now, this does not make sense at all from any way you look at it. There's been a great deal of discussion as to whether the brain structure, which is being preserved here in the so-called endocast, is effectively human, whether it was capable of cognitive sophistication. But both the tall cultures, if they're correctly identified, and the structures within the brain indicate that that is the case. But on the other hand, if you do the calculations on a brain size of that diminutive nature, it simply can't do that sort of thinking. So something here is not making any sense at all. But the straw in the wind may be as follows, and there's more than that, and this is where I'll conclude you'll be able to hear. Because again, it steps back to where is our consciousness resting. Now, of course, as you know, the received wisdom, and it may well be correct, you know, science is very good at proving things like this. But on the other hand, when science has trouble over many decades, one is entitled to say, well, maybe the question, at least in some way, has got to be reformulated. But to think of the convergence in the context of singing, I mentioned that within the birds. Now, singing has evolved independently in a whole set of birds. Did you know, for instance, purring, another sort of vocalization is convergent? Oh yeah, some monkeys purr, as well as cats, there we go. But in the male humpback whales, they too are famous for their singing. And some of their singing can be heard over very substantial distances. Now, the convergence can be explained simply in terms of the physics of sound production, vibrating columns of air, by and large. But there is an essay by Patricia Gray, who's a musicologist in Science, published I think it was in 2002. And she says, well, that's all fine and large, and I'm quite prepared, if I remember her argument correctly, that's part of the argument. But we can actually look at the convergence of singing in a completely different context, and simply say, well, the reason why the singing is the same, the reason why it's music, the reason why it's got melody and harmony, has inversion, has all the aspects which we regard as interesting and beautiful and worth listening to, even amongst animals, is in point of fact that there is, quote, a universal music. In other words, there is universal music out there, and evolution is simply a search engine. The reason why you converge is you keep on ending up in the same arrangement, because that arrangement has been there all the time. Now, if that applies to music, then in principle I don't see why it doesn't apply to consciousness as well. And you can see in that perspective, one's still dealing with a real world, but you are very much stepping into uncharted territory. So, and if that's, come on, don't be shy. If that, oh, don't go there, I don't want these silence. If that is true of music, if that is true of consciousness, then as some of you may be interested to discuss, that is very probably true of religion as well. So I'll finish there, if that's okay, Dennis. Sorry, 2 minutes over. But, and if there are questions, then I'll obviously do my best to deal with them. Thank you.
Thank you very much, Simon. Good. So I'm sure that's stimulated plenty of questions. And the first one is over here. Yes. So.
Given the high degree of convergence, both at cognitive level and molecular level, do you think we can call one species superior to other, as we generally tend to?
Gosh. Yes and no. Well, how does one begin to start? The more superior you become, let's put it this way, and I'm not an ethicist, by the way, at all. I'm a philosopher manqué, but the more superior you become, the more your responsibilities grow. So effectively, especially in science, the more we understand about the world, the more remarkable we find it. But in that sort of way, if the world is deemed, due to our interference, to be relatively fragile, which I think would be a fair point, then when one takes additional responsibility for that. So in a certain way, yes, I think I have a more interesting cognitive life than a cat would. In fact, I know that about as sure as I know anything, but that's another story. But in any event, dogs different, that's another story, because we're symbiotic with dogs. In that sort of way, don't you believe that? In that sort of way, yes, there is. If you use loaded words like scala naturae and so forth, or if you have this sort of idea that somehow one can end up looking down on things, I think that would be utterly mistaken. And of course, as you might agree, in certain hands, the idea of some sort of racial superiority in particular has been exercised several times in living memory to absolutely disastrously, to put it mildly, in that sort of way. So there